create in the lab, known as tholins, are about 2 microns in size, and then the clusters that they naturally create are about 10 microns maximum. So this is kind of visualization of the difference in size that you need. I swear in this box down over here in the left, there is one, like our 1 micron particle. And then if you go to the minimum size by theory, that's pretty much the difference that you have to make. And then if you go kind of to the maximum, so you can see it's about 1,000,000 and 1,000,000,000 times more volume, even though it's about 200 to 1,000 times more size. So Jason Barnes, Jason Barnes et al. In 2015, they published a paper kind of exploring how you can grow these particles to be sand-sized. And so they explored 2 that are dry methods, sintering and lithification, and then 2 that are kind of aqueous methods that require liquid, flocculation, and evaporative deposition. So I should talk about the analogs that I have said before as well. This is the analog session after all. So what we do is we kind of take Jason's idea and we make these analogs in the lab. So the picture on the left is our tube. You fill that with the gas and nitrogen and methane from Titan, and then you kind of run a plasma in there that kind of simulates the space environment around Titan. So the energetic particles from Saturn's magnetosphere, or cosmic rays, or UVA radiation. And you create these tholins on the right, which are the analog for Titan's organic haze. And so what we do here is, so that was a figure from before. We use those analogs, and we use hexane, which is our analog for the liquid hydrocarbons. We do it at room temperature, and we mix those, and then we see can interaction with liquids grow those particles. So we're exploring the aqueous only part of Jason Barnes's paper. I will justify hexane here a little bit. The surface tension of liquid methane at Titan temperature is about 17 or 16, but the surface tension of hexane is about 18. And surface energy and Gibbs free energy are like directly related. So we kind of infer some similar thermodynamic properties. It's not the perfect, but it's pretty good. We think it's pretty good. So, and then previous work trying to see this aqueous interaction from Hirai et al. 2023. Basically, they interacted it with liquid methane at Titan temperature, and they just did a simple wetting and drying. And so on the left is one of their figures from the paper where they showed the aggregates kind of before. And so you see kind of the natural clusters are about 5 microns in size. And then on the right is after they just wet it with liquid methane and then let it dry. And basically, they say it grows up to about tens of microns, 10 to 20 microns. So what we know from this paper is that just simple wetting and drying is not enough to create those dune-sized particles. And we think this is because you need turbulence. And so turbulence is a very natural phenomenon, especially on Earth. If you've ever been whitewater rafting, and research on Earth has shown that flocculation might be improved or might even require turbulence. So what we're doing is we're kind of taking that experiment of wetting and drying, but we're also adding this turbulence while we do it. So you're going to see these pictograms a couple of times here. We do 6 experiments. These first 2 are the no mixing experiments. So for 30 minutes, we just let our analog sit in the liquid hexane, and then we kind of take it out, we look at it, and then we also have another one where instead of doing it for 30 minutes, we just let them completely dry. We let the whole hexane evaporate. And then we also have 2 others. So again, 30 minutes, but with mixing. And then on the right, again, full evaporation with mixing. And then for the 2 where we have 30 minutes and we have still a whole bunch of hexane left over, we kind of separate that liquid, but leave all the solid. And then we try to let that evaporate on its own. So 5 and 6 are kind of the separation. And that'll be like testing the evaporative deposition that Jason Barnes was talking about. And so say hi to the camera. So this is our experimental setup. It's a little crazy, I will say. So there's a clean wafer on the bottom, and then those kind of brown powders you see are our sample. And then we also had another setup on the edge for like the coffee rings as things dry for those experiments. I will not be showing this stuff on the edge. It's just too much. So we'll start with this. So that's what the blank clean wafer looks like. So the 30-minute with no mixing kind of looks like this. And then with mixing, and you let, well, no mixing, but you let it evaporate. It's a little bit different. You can see there's a little bit of clustering. And then once you add mixing with turbulence for 30 minutes, you can definitely see the clusters. And then the 4th one where we mix it completely kind of did not really work out for us, so I won't be talking about it. And then I will be showing these 2, the evaporites from the 2 30-minute experiments, but we won't go over them. They formed a film, so it's very hard to see in scanning electron microscopy, so we don't show it here. It wasn't very conclusive. And so here are the powders in scanning electron microscopy. This is a scale is 500 nanometers in the bottom left. And so our unaltered powders before touching any liquid are about 0.5 to 2 microns. And the monomers, so like that on the biggest one on the left, you can kind of see this texturing. Those smaller are the monomers, so 200 to 100 nanometers. And so this completely agrees with what we've seen before for the analogs and on Huygens. And the natural clusters they create are about 10 microns. The biggest one I could find is the red arrow there. But they're very loosely bound. It's not very well put together, basically. And so for just 30 minutes of no mixing, so the scale here now is 100 microns instead of 500 nanometers. So we counted a couple hundred of these. The median is about 70, but the largest one I could find was about 1 millimeter, 1380 microns. So we do see some growth, just like ADO did. But we agree, simple wetting and drying is not enough, at least for the median. And then if you zoom in on some of these particles, you can see they are still, these big clusters are still created of those 0.5 to 2 micron particles. And then if you do it until it evaporates, you kind of get a better median, so it's about double. So time here might make a difference. That's the biggest one I could find, 659 microns. So sometimes the maximum is a little bit lying to, in a way. And then once you include mixing, the median basically doubles once again. So now we're within the theoretical range of 200 to 1,000 microns. And so that's the biggest one I could find, 1701. And the median is about 300 here, and the scale is 200 microns for this image. And so when we do, oh, my colors went away. Well, these had colors at some point, but I guess not anymore. When you do the mixing, so the red one is 30 minutes no mixing. You can see the kind of peak shifts once you allow it to evaporate. So we think time in the liquid plays a big difference. And then once you add the mixing, that's even more important than the time. So once you let it evaporate, pretty much once you let it evaporate, the time that it's in that liquid does not matter as much as mixing. So we think mixing is a more important factor here. And so this basically passes like a visual check here. So you can see kind of the clusters and the grains are getting a lot bigger. So no mixing until evaporation, no mixing, and then 30 minutes of just mixing. So it kind of passes your visual test. And so one comment we got when we were talking to people is maybe the kinetics. So the temperature, Titan is a very cold place. So we kind of have to think about it. So the easiest way, obviously, just stick it in a fridge. And so once again, the blank wafer. And then once again, 30 minutes with no mixing until evaporation with no mixing. 30 minutes with mixing, we don't do number 4 again, and then our 2 separations, once again, that we won't talk about because we think it made a film. And so when you go through the images, once again, so the median here is actually pretty small, only 17, and that's the largest one I could find, 259. And then once you let it evaporate, the median basically double 10 times, and the one in the circle is the biggest one I could find, 375 microns. So once again, time is making a difference. And then once you do the 30 minutes with mixing, it doesn't double, but it's 153 microns, the median, and that's the biggest one I could find, 1323. So here it's a little bit different, where now we're not even in the theoretical range anymore. Shit. But basically, to conclude, what we want to say is the temperature does kind of shift your peak, so you do get a dependence on the kinetics. And so I'll kind of just leave you. Well, we want to do future work. We want to do the mechanical properties, and then this is the conclusion. Thank you.
Thank you. Our next speaker is Samuel Harris, who will be talking to us about radar reflections of packets of sub-resolution dust layers within ice in Martian analog experiments. Take it away.
Good morning. My name's Sam Harris. I'm a first-year PhD student at Purdue University, and today I'm going to talk to you about how we can build laboratory analogs of the Martian polar layer deposits to better understand our radar observations of them. But first, let's go to the polar layer deposits. These are 2 to 3 kilometer thick ice and dust deposits located on both the north and south poles of Mars. And these are believed to contain a rich record of the Martian paleoclimate, which is driven by the obliquity of Mars. So currently, Mars is at a 25-degree obliquity, where ice in the poles is relatively stable and we're believed to be in a period of accumulation. However, Mars exhibits extreme obliquity shifts from 15 to 60 degrees. And so when Mars gets higher obliquity, the poles get more direct solar radiation, and ice becomes less stable at the poles and more stable at the lower latitudes. And so when Mars gets lower obliquities, ice becomes more stable at the poles and less stable at the lower latitudes. These periods of ice stability regimes are believed to be captured in the polar layer deposits, similar to how sedimentary records on Earth can show us the paleoclimates on Earth. So an example, visual example of these PLDs. So here we can see the different dusty and ice layers, similar to what we see on Earth with sedimentary-like layers. So these are visual observations, which presents a problem. As I said earlier, the PLDs are around 2 to 3 kilometers thick, and visual, we can only get outcroppings. And so what we use to probe the 2 to 3 kilometer thick polar layer deposits is radar, which present an almost ice core-like remote sensing. And so each of these bright reflectors we see are a change in the physical characteristics or the dielectric properties of these materials. Here it's believed these are to be the internal layerings or differences in dust contrast. And so SHARAD, the shallow radar instrument on the Mars Reconnaissance Orbiter, has a vertical resolution of around 10 meters. This is primarily a function of its wavelength. But as we can see from visual observations, we have a strat column here showing centimeter to meter scale dust layers. But vertical resolution of SHARAD is 10 meters, so this presents a problem. Just because these layers are below the vertical resolution, they still have an impact on our radar observations. So figuring out a way to connect these sub-resolution layers to vertical and radar observations is key to understanding how the Martian paleoclimate developed. And so that's where my experiment comes in. We build a series of different stratigraphies and different thicknesses and spacings of dust and ice layers. Here we use a Martian regolith simulant, MGS-1, and water ice, and we can put it into a 72 by 72 by 45 centimeter plastic box, and we can put it into a -20-degree freezer. And so we use it off-the-shelf commercial radar system with a center frequency of 2.7 gigahertz, which gives us a wavelength in free space of around 11 centimeters. And we use this 11 centimeters as sort of a starting point or a guide to develop our layer thicknesses. So as you can see in the top left here, we have thicknesses of 1/2 wavelength, which is around 5.5 centimeters. And then we have 1/4 wavelength, which is 2.75 centimeters thicknesses, and then 1/8 wavelength, which is around 1.38 centimeter thicknesses. And so these dust layers we see here, they're not 100% dust. That is because the porosity of the regolith. And so these layers here in red are around 50 to 55% dust and the rest water ice. And so in total, I plan to test around 64 different layer and thickness spacing and thickness combinations, all the way down to wavelength over 16 thicknesses and spacing, which is around 0.68 centimeters. And so I've only gotten through a few of my experiments, so I'm going to tell you about some interesting findings we have. So first, we're going to focus on these single layers. We have a 1/2 thick dust layer, which is around 5.5 centimeters, a 1/4 thick dust layer, and a single 1/8 thick dust layer. And so if we pull up a radargram of the 1/4 thick dust layer, or 2.75 centimeters, we're going to get this top reflector here, which is the bright red-blue pair. This is the top of our experiment. So this is where the air-ice interface is, and we get a large dielectric contrast. But as we propagate through the experiment, we're going to get these two reflectors here, and this is where the ice meets the dust, and the dust meets the ice. And so we can see clear reflectors in all of our experiments of this single 1/4 thick wavelength dust layer. And these bottom reflectors here are just the bottom of the experiment where the bottom of the freezer is metal. And so there's a large dielectric contrast. So we can see clear upper and lower reflectors in this 1/4 wavelength thickness layer. But if we pull up the 1/8 thickness layer, we again see this bright air-ice interface. However, as we propagate through, we only get a single combined reflector in all of our radargrams. And again, this is the bottom. So this tells us that there is some critical thickness for detecting an upper and lower limit, and that is between a 1/4 wavelength and 1/8 wavelength thicknesses. And so for a more quantitative analysis of this, here are just the stratigraphies I brought up just for clarification. We have the 1/2, 1/4, and 1/8 thicknesses. So we can look at the power returned. So this is a function of power return, so the transmitted power, and then we get the return power from these reflectors. So at the bottom on the x-axis here, 0 indicates 100% of the transmitted power is returned. And so we can see in the 1/2 and the 1/4 wavelengths, we get similar power returns at the upper and lower reflectors, but we get this combined reflector of the single thin dust layer. So using these results, we can take this back to these multi-layer experiments and kind of constrain the non-uniqueness of radar data. So I'm going to talk to you about a single 1/2 thick dusty layer and two 1/8 thick dusty layers spaced 1/2 apart. So in this one on the right here, we're going to get the combined reflectors. So they're going to look similar in radar reflections. And so I'll just talk to you about the power returns of these two. And this is just for your own sake, for clarity. We have the 1/2 a thickness, and then we have the two thin layers spaced that same thickness apart. So this is where the interesting result comes in, where we can see this top reflector, we get similar power returns centered around this like -5 dB mean. But if you look at the single thick layer, we have a power return of the lower reflector at around -10. However, in the thin layers, we get a power return of around -5. And this is an expected result because ice is a low loss material compared to dust. And so as the radar wave is propagating through this ice, it's losing less power. And so this is good news that our experiments are working and we're seeing what we're expecting. And so tying this all together, we can determine a critical thickness for distinct upper and lower reflectors of a dusty layer, which is between 1/4 and 1/8 the transmitted wavelength. And then we can use this single thick dusty layer and we can differentiate it from multiple thin dusty layers based on the power return of the lower reflector. And so there's a lot of future work planned. However, most of that starts with just finishing the rest of my experiments in different combinations and thicknesses. I plan to use real observations in the future once I'm done to connect the visual to the radar observations, and hopefully my experimental results will match what we see in the future. And so hopefully once I'm done with this, we'll be able to connect our visual radar and unlock the Martian polar climate. Thank you.
All right, thank you. Our next speaker is India Riddell, who will be presenting Exploring Phosphorus and Sulfur Speciation in Extraterrestrial Materials in Contrast to Manufactured Martian and Lunar Regolith Simulants via synchrotron-based X-ray microscopy. Take it away.
Yeah, the clicker. Oh, is this it? Oh my gosh, goodness. I'm so sorry. Hello, everyone. My name is India Riddell. I am an undergraduate student at Texas A&M University. And today I'm going to be discussing my research on exploring extraterrestrial materials in contrast to manufactured regolith simulants via synchrotron-based X-ray microspectroscopy. Thank you for bearing with that very long title. So the 3 different parts of my presentation that I'll be going over today. First, I'll be talking about the relevance and why it is important to look into these different nutrients and these extraterrestrial stimulants according to agricultural use. And then I'll be talking about the methods and technologies that we used. And then finally, I'll be wrapping up with our conclusions and analysis. So the objective of the study is to investigate phosphorus and sulfur speciation in these simulants because these species directly correlate to the ability for plants to take up these nutrients in these authentic extraterrestrial materials. So some more relevance is that the in situ research resource utilization of these nutrients and these regoliths as we go to these different planetary bodies, it is very important that we know what's in there, these regoliths, and that we can use them so to minimize our payloads, and so that we can't be bringing all this soil to these planets, obviously. So it is very important to look into these at these minuscule nutrient levels. We also have seen that there is a lot of studies that are using these regolith simulants as substrates in these plant nutrition studies. So again, it is very important that these regolith simulants provide a genuine representation of these extraterrestrial or their counterparts. So I collected my data at the National Synchrotron Light Source, NSLS2, in Uptown, New York. And I'm going to be diving into what beamline we used and its capabilities, the samples that we decided to run and its mounting, and then the data we collected. So the beam we decided to go with was the 4BM X-ray fluorescence microprobe, or XFM. This is a very novel microprobe. It's able to operate across tender and hard X-rated elements. Like it can do phosphorus and sulfur, but it can also reach these harder elements like iron and calcium, which is very important for our research. It shows the elemental distributions and chemical species within these heterogeneous systems, and this is why we decided to go with this very novel beamline. These samples we decided to run, we chose one lunar sample, regolith simulant, and 2 Martian regolith simulants. The lunar South Pole 1, Johnson Space Center Mars 1, and Mars Global Simulant 1. And we decided to go with the Powder Mountain method. This is because we are able to see the soil surface, and this is very important because the surface of these particles will provide us adequate information on the plant available species as we are continuing this work. So how this kind of set up, I put my samples in the beam and we found its correct positioning. We ran these these energy specific maps on the soil surface. Over here, you can see that these maps on the soil surface, the phosphorus is correlated to red, the sulfur is correlated to green, and the iron is blue, as you can see up here. Just through visuals, we can see the different collocations and distributions of these elements, and we can do these fine-tuned mappings on each area of interest. And from that, we can kind of find the point where it has the highest counts or concentrations of the elements that we're interested in. And we can run these microzanes on these points, which give us pretty much a fingerprint of what species is there. After such analysis or a collection of data, the analysis that we'll be using is the spectral feature analysis. This analysis is fitting a series of Gaussian peaks and Lagrangian functions underneath our Zane species. This is a more adequate approach to fingerprinting and does not overfit and accounts for all these subtle features in phosphorus that linear combination fitting usually misses. So now I'm going to go into my conclusions and results. So the first regolith that we looked at was the lunar South Pole. Again, phosphorus is going to be in the red, sulfur is going to be in the green, and iron is going to be in the blue. We can see that, so this is the large map of the soil interface, and then here are the smaller maps that we took off. This is partial data here, and these are the zanes that we've seen through these maps. So when we want to look at the phosphorus zanes, as we can see over here, both phosphorus zanes that are in this part of the map are the calcium apatite species, as we can see with these indicative post-edge features. In the literature that I have looked at, phosphorus is actually more abundantly seen as apatite in these lunar samples. So this seeing these apatite species in this regolith was very on par with what I've seen in literature. If when we look at the sulfur zanes, we could see that the sulfur peak was at the 2482 EV. So we knew it is a sulfate species, and it's an iron sulfate because we can see that indicative pre-edge feature. However, in literature and what we've seen from these lunar samples, sulfate is actually, or sulfur is actually seen more in a stable sulfide form. And though there are sulfates, it's going to be, we did not see any sulfide in this sample. Now we can look at the Martian regolith simulants. So the first one we looked at was the Johnson Space Center Mars 1. The colors correlate again to the same section. For the phosphorus species, we found an aluminum phosphate and a iron phosphate. P is actually more abundantly found as apatite in these Martian meteors that we've looked at, and also in what we've kind of seen through rover findings. So we did not see any of these apatites, though we did see some iron, which has been discussed recently that there would be iron phosphates in the Martian soils. When we would jump over to the sulfur zanes, sulfur was seen as an iron sulfate species. Again, in these meteorites, we've actually seen more stable forms of sulfur in the sulfide form. Though there are sulfates, the primary concentration has been in sulfide form, and we did not see that. Finally, our last simulant that we looked at was our Mars Global Simulant 1. This one was very interesting. For the phosphorus, we saw a iron phosphate and then many apatite species, which is very in line from what we've seen in these meteors, which is the primary kind of concentrations of these apatite species and this low concentration of these irons, which is very interesting. For the sulfur, again, it was a sulfate iron species. And again, we did not see any stable forms of these sulfides. So in conclusion, in terms of phosphorus speciation, the MGS-1 is more similar to the expected Martian lithic material than the JSC Mars-1, and both Martian simulants lacked the correct and kind of concentrations of these sulfide species. For the lunar sample, the LSP-2, it provides adequate information on the representation of the P species, although no sulfides were present in this regolith. And then also from the overall kind of research, we can also say that the Martian and lunar lithospheres are a pretty good potential in situ resource of phosphorus, sulfur, and calcium. And but it is very important that these plant nutrition studies, which utilize these simulants, do take into consideration these similarities and differences as they run through their research. But yes, thank you all so much. I'll take questions at the end.
Wonderful, thank you. Our next speaker is Pratik Tripathi, who will be presenting on spectral comparison of synthetic and Apollo glasses, applications to interpreting remote sensing observations of the moon. Take it away whenever you're ready.
Morning, everyone. I'm Pratik, one of the LunaWise postdoc at UCF, and today I'm going to talk about comparison, a VNIR spectral comparison of synthetic and Apollo glasses and their application to interpreting remote sensing observation of the moon. So why we need to study lunar glasses, especially a synthetic glasses? Because they serve as a critical time capsule for the lunar geological history. Also, their composition diversity in lunar volcanism, basically the TI content variation reflects the interior heterogeneity. It was reported in the literature that there is a TI content variation among the lunar glasses. Also, if you see that if we have synthetic glasses, they can serve as a control reference point or a footprint for spectroscopic analysis of lunar volcanic materials. And it can also answer the questions, what is the global variation of lunar pyroclastic deposit composition? So coming to this work has 3 parts. First one was to synthesize glasses with systematic composition range in iron and titanium. And the second one is to spectrally characterize the synthetic glasses and Apollo-returned lunar glasses. And the third one is to interpret the composition of lunar pyroclastic deposit using remote sensing observation and our laboratory measurements. So coming to the methods, okay. I hate this part, but yeah, we crushed the samples. I mean, this was my first week of post, and my boss told me to go in the lab and crush the samples, the glass samples, and we have only 2 grams of samples, and we have to save most of it. Yeah. So yeah, we crushed it, washed it, sieved it into 5 sections, less than 45 micron and 125 to 250 micron. Then they were sent to the relab at Brown University to get the VNI spectra using BDS bidirectional spectrometer. After we got the spectra, we calculated some traditional band parameters for now. It's like including the 1 and 2 micron band centers and asymmetricity. Also, we analyzed the peak position near 0.6 or 0.7 micron. So here are some classes, some spectra. So this is 45 micron synthetic glasses spectra. On the left side, the green, you can see the green samples Apollo from ranging from Apollo 11 to 14 and 15. And here you can see titanium was fixed for 0% and iron was varied. On the right side, you can see the samples where titanium was varied and Fu was fixed around 20%. So there was a poster on Tuesday how these glasses were synthesized by Preissel et al. At JSC. And if you didn't go to the poster, you can look at the abstract also. Similarly, you can see here, these are the 125 to 550 micron synthetic glasses, and there's a difference in the reflectance. Previously, it was around 0.3, and here it's like 0.7, probably because of the particle size. And here also, these are the zero titanium fixed iron varied samples. This is a titanium series with titanium varied and iron fixed samples. Also, there is a change in the peak here. For seeing the change in the 1 and 2 micron, I will show you some band parameters. So this is the first band parameter plot. So we plotted band center 1 against the 1 micron asymmetricity. Here you can see I put these two graphs are the same, but I put the color coding different. This is the iron composition color coding, and this is the titanium. You can see all the green classes with 0 titanium, they are grouped together, and the higher FeO or lower TiO2 sample tend to cluster here. Also, if you look for 1 micron, the asymmetricity goes up to 14%, and there is no iron trend, FeO trend. But if you go to the 125 micron, 2 micron band center graph, here we see the same trend, but the asymmetricity barely goes up to 12%, which is lesser than the 1 micron. Also, coming to the peaks of 45 micron and 125 micron, you can see that I plotted against the iron content and the color codings as per the TiO2 content. So as we see, as the peak is shifting to the longer wavelength, the titanium values increases for both 45 and 125 microns. So it reflects the more the steeper slope we have in this spectra, more is the iron and titanium interaction in the classes. These are the synthetic glasses. So to compare with the Apollo glasses, we have extracted all the possible Apollo glass spectra from the Relab database. And you can see here that Apollo 12, 15, and 16, they are mostly impact met, but Apollo 17, the orange one and the black one, they are the actual glasses with some of the mixture. So most of the analysis was focused on all the glasses, but we will specifically focus on the Apollo 17 glasses. Here you can see the 1 micron band, the peak, which is similar to our synthetic glasses, and the 1 micron band is here with a broad, almost no 2 micron band. So now we plotted the band center versus band center, the both band center and band center versus the 1 micron and 2 micron asymmetricity. So here you can see the green and blue are the synthetic glasses and red one are the Apollo glasses. So we found some similarity for band center for Apollo 15 green glass, which was close to the Apollo 15 actual Apollo glasses, written glasses. But we didn't see any trend in 1 micron asymmetry, but we did see a proximity of Apollo 17 orange glass, the actual Relab glass with our synthetic glasses in 45 micron. So to complete the analysis, to put in the context, we extracted all the Apollo glasses sampling site spectra from orbital moon mineralogical mapper data from Chandrayaan-1. You can see this is just I'm showing just for one location. You can see the Apollo 17 travels with station 4 just below the Shorty crater. Here's the Shorty crater, and we just put the the control points, the coordinates, and we found that Apollo 17, 74220, the orange one, and 74002, the black one, they are following on the edge of 2 pixels. So we took both spectra here, and we plotted against those plots, including the Apollo glasses, the M-cube sites. Actually. So black one are the M-cube sites. So here you can see, we see Apollo 17 orange glass, which was the only pure orange glass sample, has a close net or similarity or inconsistency with the 45 micron and some of the Relev Apollo glasses. Also here you can see some similarity with Apollo glasses and an M-cube Apollo site. So here you can see it, the 1 micron band symmetricity ranges up to 60%, and here the 2 micron 40%, which is consistent with the 2 micron band being flat in actual Apollo glasses. So coming to the final side, we found that VNI spectra for both synthetic and natural volcanic glasses have distinctive spectral characteristics. That's why their band parameters were ranging. Also, particle size does affect the VNI spectral shape, because there was a difference in the peak and also the band centers. And there is a greater diversity in Apollo glasses spectral shape, which is obvious because they have been subjected to a lot of process on the lunar surface. And we also observed the similarity between M-cube remote sensing observation of Apollo glass sampling and laboratory spectra of Apollo glass and our synthetic glasses. And we will be continuing this work. We have the MIS spectra, we have CF features. We are going to integrate them with the diviner and cargo data, and we'll continue our analysis. So thank you very much.
Okay, we're actually running a little bit ahead of time. So we have about a minute until our next speaker can begin. So I'll just take this time to remind everyone that we'll have a Q&A session with all of the panelists at the end. So please stick around to ask all of your questions at the end. Okay, so our next speaker is Kayla Lacovino, and the presentation is Filling the Redox Gap, Enabling Experiments on Reduced Planetary Bodies with Low-Cost Steel Alloy Buffers. Take it away.
All right, thank you very much. So I just want to say this has been a really great, very diverse session. So I'm excited to talk to you guys about experimental petrology today. And I want to make sure to point out that all the work I'm showing today is by Noah Collin, who's a master's student at the University INAS de Lyon. So big shout out to him. This is all of his work. I'm just presenting it on his behalf. And just a quick note that he was an intern with myself, Johnson Space Center this summer as part of the NFAR program, or the NASA Facility for Astromaterials Research. There's a QR code there. It's a relatively new program. And a great way to be able to get people to sort of hook up with Johnson Space Center and use our facilities for no cost. So experimental petrology, this is what we do in our lab. We basically make planets in the lab at high temperature and high pressure. This is an instrument that we have. We have 3 of these and some other instruments. This is called a piston cylinder. I describe it to people as basically a car jack on steroids. It's a hydraulic pump. And then we heat it through resistive heating. So this one in particular can do up to a couple thousand degrees Celsius and high pressure into the mantles and cores of planets. Inside of this core in the center there, which is highlighted in the green color, that's the pressure core. And our sample assembly sits inside of that. So this is going to get progressively smaller and smaller until we get to our actual sample, where we have basically a series of things that are spacers. We have a tube of graphite, which we run a current through to heat the sample up to 1600 degrees. And then our sample is in this red box here in the center. And this is where the magic happens. And we're having some kind of a sample in there that represents material from a planet. Typically, we're looking at igneous material, so we can reproduce the processes that are happening inside these planets. So now really quickly to describe a very fun concept called oxygen fugacity. So this is a chemical term. It's basically a description of how much oxygen is in the system that's available to react. And because oxygen is a huge component of silicates, materials that make up our planets, this property is really, really important to tell us if an element will be as a metal or as part of a silicate melt, for example. And we can know what the FO2 is if certain phases are present. So a famous example of this is rust, iron, and iron oxide. If you're in low FO2 or a reducing system, which would be on this graph to the left, FO2 is in low values. You're going to have a metal phase. If you're on the right-hand side, you have more oxygen available, and you're going to be in the oxide phase. So in our experiments, we can control that value by placing those components in next to our sample. If both of those things are present at equilibrium, we fix the oxygen fugacity. And we also talk about them based on these buffers, so iron and iron oxide, for example, because it gives us a frame of reference rather than citing this number, which is actually a log scale. So we don't want to talk about, 10 to the minus 12. We talk about it, how far are you away from one of these buffers? This is a typical sample capsule where we have those two components inside of our capsule next to our silicate melt sample, but we're going to do something a bit different here. And instead of using the reaction between those buffers, we'll use the reaction between our sample itself and the capsule material. And so you'll notice here in this chart on the right, there's this big space between the chromium and the iron buffers. And that's where a lot of important things happen for nebular chondrites, Mercury, and even some of the reducing parts of Mars. And so stainless steel, 304, very easy material to obtain, very cheap, actually has all of these components on either side of that gap. So our question was, can we use the reaction between stainless steel and our silicate sample to get oxygen fugacities in that really important part of the oxygen fugacity scale? So again, sort of here's a look at that reaction that we're testing. Again, the top would be a simple system. Of course, a difficulty with our setup is represented by the bottom, two very complex multi-component systems. We don't know all of the thermodynamic properties of each of these components. And it's also going to depend, this reaction is going to depend on the composition of our sample. So there's a lot of things we need to understand to see if this will work. These are the two rock samples that we used. We used one from an analog, not the actual 15555 sample, but an analog of the 15555 Apollo sample in the orange, and then an Antarctic igneous rock in the green there. And so I'm going to show you some of the results first optically. So just looking after these experiments come out, you can see the capsule in the top there. On the left is after the experiment, on the right is before. So we squish it and we heat it, and then NOAA would slice it in half, and under the microscope, visible light, it would look like this. You can immediately see this for the geologists and metrologists in the room. That's a reaction rim very clearly here, that discoloration between our silicate sample and the metal capsule. And then we would take that and put it on the microprobe. And this is the same exact sample on the right in an electron backscatter image from the microprobe. And you can see that reaction rim is the same there as what you're looking at on the left. And I'll show you some more examples of those in a second. So when we take a bit of a zoom in and see what's happening at the interface between the melt and the capsule, you can see that the bright shiny thing there, the brighter color is the capsule, and those dark bits are actually pieces of chromium that have become immiscible. They've come out of the steel itself and formed chromium-enriched blobs of stainless steel. And at these higher temperature experiments, we actually hit the melting point of the steel, and you start to see these droplets of molten steel dripping down into the silicate melt. And this becomes very important, clearly. So again, here's a sort of a look at the temperature series that we did. And you can see here, I'm going to outline this now for you like that. So you can kind of see that there is this reaction rim from low to high temperature that progresses inward towards the center of the capsule. So at the very center of our sample, we are pretty much unreacted, and on the very edges, we're highly reacted. And this is a temperature-driven, so kinetically driven process that's slowed down by how hot our system is, how fast can these elements diffuse. And so NOAA did a set of transects on the microprobe to look at the composition across that boundary between the steel and the silicate. And this is some of the results here. And you can see this is in chromium as a distance where 0 is the boundary between the capsule and melt. And you can see the chromium dropping off dramatically in the metal towards the silicate and then spiking in the silicate and then dropping back down. And so the original chromium composition was in parts per million. It was very, very low. And I'll draw your attention to the fact that we got up to 30 weight% chromium in the silicate melt, which is like crazy high. And so it turns out at these high temperatures, not only does the capsule melt, but even below the melting temperature, steel loses what's called its austenitic properties and essentially just sheds chromium into the melt. And so we see that what's actually driving this reaction is the chromium also reacting with the iron. So I wish I could go backwards. Can I? Yes. Okay. So we actually have chromium in our metal coming out, forming these chromium spinels, dumping into chromium oxide in the melt, and it's grabbing that oxygen from available iron oxide. So we're reducing our silicate melt, we're oxidizing our capsule. So this is telling us that we're very far out of equilibrium here. I mean, all of these thermodynamic calculations we need to do require the assumption of equilibrium. So what we've learned from these is that this reaction is very strong. So it's this exchange reaction between the oxygen in the silicate driven by that chromium is very fast. And so this means that it has the potential to be a really good way to set the oxygen fugacity because we can force that reaction to happen. The other thing we wanted to point out is what a savings. Normally, we have to use these inert metals like platinum and gold, and those prices can fluctuate wildly. In the case of 304 stainless, this might give us a way not only to study these really important regions of our solar system, but also to allow more people to easily obtain materials and hopefully be able to do more experiments in places that are limited otherwise. So the next thing to do really is to focus on experiments starting closer to equilibrium and with lower iron content so that we don't have to overcome that huge thermodynamic barrier in order to get something in equilibrium at those exact conditions that we need. So good first step, basically. All right, thank you.
All right, thank you. Our last speaker is Mike Lucas, who will be presenting, who will be presenting geotechnical assessment of trafficability on regolith or GATOR project, evolution of regolith geotechnical properties during repeated rover wheel traverses. Take it away, Mike.
Thanks, Audrey. I'm pleased to have the distinction of being one of the final talks of the 56th LPSC, and so they do save the best for last. But anyways, it's a pleasure to help take us all home. And so Audrey mentioned the title, and you can see the large team here, most of which are associated with the University of Central Florida in some way. So a brief outline. I always like to start out presentations with why do we care about this work? Why are we doing this? And so then I'll get into methods regarding cone penetrometer testing. And I'll use CPT hereafter in the talk for that. And then I'll get into methods regarding the Ryder Terra Mechanics facility. And then I'll give a overview of the GATOR project. And, you know, I might have to rethink this name. I went to the University of Tennessee, so I don't know what I was thinking when I named it this, but it's all right. It fits. And then I'll give some results about the GATOR project, CPT results from the project. And then I'd like to indulge myself and give shameless plugs for two of our facilities at the Exolith Lab for lunar analog testing. And so let me jump right in. And so long duration stays on the lunar surface are going to require investigations into the trafficability of the lunar surface. And trafficability means the capacity of a soil to support a vehicle and provide sufficient traction for movement. And on the image here, I put up I put a question mark here after road construction on the moon because, you know, how do we most efficiently get around on the lunar surface? I don't think it's quite been worked out yet. You know, do we build roads? If so, how do we stabilize them? Or is it more efficient to drive over previous tracks or not? You know, so these are the types of things that are important to consider. And these activities will demand a firm understanding of the geotechnical properties, structure, and stratigraphy of the near surface regolith. And, you know, about half of our team are geologists, you know, and so we kind of approach the problem from a geological perspective of, you know, most trafficability studies are performed by engineers looking to design a better wheel or a better rover. You know, as a geologist, we're interested in rocks, minerals, soils, and these types of things. So our idea was what happens to the geotechnical properties of the soil of the regolith during repeated wheel traffic on the moon. And so that's our motivation. And let me go on. So some methods now. And we use, oops, I'm sorry. I was trying for the highlighter there. We used a RIMIC CP40 cone penetrometer, and this method's based on the failure mechanism associated with wedge penetration, you know, through dense soils. And on the left, you can see a small scale test that replicated two-layer stratigraphy that was measured in situ at the Apollo 16 landing site. A dense layer here, but an even denser layer at about 20 centimeters depth. On the far right, you can see a plan view looking into the bin, and you can see the Purina pattern of our 5 CPT insertions to measure, which you get the data is these stress versus depth curves here. And from these data, we measure the G-slope, which is simply the slope of stress over depth for these curves. And so with these data, you can actually develop correlations between penetration resistance on the slope parameter and bulk density of the simulant. So this left plot shows 45 CP insertions, 9 different packings, 5 CPT insertions each, and you can see that there's a strong exponential relationship, note the log y-axis there, between the slope parameter and bulk density of the simulants. We can effectively sense the density stratigraphy as we're going through the surface. And on the right, here is that packing I just showed in the previous slide, penetration depth versus stress curves. And the blue is the laboratory data. The black is the laboratory data with a reduction factor of 0.29 applied in order to adjust for lunar conditions. And then the gray I've plotted in situ data from Apollo 16, Station 4 and 10. And you can see we're replicating that stratigraphic profile pretty nicely. And so now I want to, there we go. I want to introduce the Ryder Terra Mechanics Testbed facility at Exolith Lab. Gator project was performed in this. This is a single wheel, a linear rover wheel test facility that we designed and developed over about a year and a half. We've been in operation almost 2 years now. But yeah, mobility is challenging on planetary surfaces. The terrestrial soils and the conditions on the Earth are a lot different than planetary environments. So I list some of the things that are important there to consider. So there's a need to test rover wheel performance, or as geologists investigate the regolith, in accurate analog conditions. And so, and then I don't have time to go in. There's a lot of subsystems involved with Ryder, and I don't have time to dive into them, but there's some of the features there that we have. And so a Gator project overview. And so you see here in these pictures, this is the Ryder test bin. And you can see that we significantly scaled up the 2-layer density packing that I showed you in the previous slide on a much smaller scale. So we did replicate the 2-layer stratigraphy in the Ryder test bin. And that's about 2 metric tons of simulant to create that 2-layer stratigraphic profile. And then so with that, we tested 3 prototype lunar rover wheels in the bin, performing 900 passes each wheel, and then pausing every 100 passes to test the geotechnical properties of the simulant and perform CPT measurements. And so, by far the coolest is the Apollo LRV replica. This is one of 12 that exists in the world. We were lucky enough to get one on loan, so acknowledge to the Glenn Research Center. But we did, I'm going to show you results from the, not allowed to call it a Viper wheel, it's got a Viper-like wheel, the Resource Prospector heritage. And so I'm going to show you CPT results for this. But here in the tables, I apologize for the tables on the slide, but here you can see some of the rover gross masses and the lunar loads, and also the test speeds that we tested for these wheels. And then, like I said, I'm showing you CPT results here. We have a large data set of particle size distribution samples at every pause, and also samples for particle shape analysis. I only got 10 slides to go, so, okay, yeah. But anyways, yeah, so particle size distribution samples and particle shapes are still being investigated. So that work is forthcoming, still being reduced and interpreted. And so there you can see the wheel in action in Ryder. And here's a map view of the simulant bed with my insertions. The red asterisk or the baseline, that means before any wheel passes. The blue are in track after every 100 passes, working in from the ends in duplicate, and the orange show the outside track in the same pattern. And so let me move on here. So the left shows inside track G slopes for both the upper layer, the blue crosses, and the lower layer, the blue circles. And you can see there's an evolution of the G slope properties correlate with the density, like I showed earlier in the compaction of the simulant. And on the right side, interestingly, the upper layer kind of doesn't change from it hugs the baseline there, so it's not really affected, but the lower layer is. And so here are penetration depth versus stress curves. Again, red is baseline, blue is in track. It was too cluttered to show all 9, but I've showed 300, 600, 900. You can see a clear evolution of the stress profile. And what I'm going to do is I'm going to overlay the outside track. And you can see that the upper layer is kind of unaffected, but you still, outside the track, the lower layer is, and I'll flip this back and forth a little bit. And then I just want to take the last opportunity here to give promotional plugs. If you didn't get a promotional flyer for Ryder or Crater, I've got some more here at the bulletin boards. And so there again, I don't have time to talk about the features here. And then of course, Crater, the world's largest by volume Lunar Highlands regular test bin, holds 125 metric tons. So hire us, come down and play on the lunar surface, or test your wheels at Ryder, or test your hardware in Crater. Thank you very much.
Thank you. All right. I would like to invite our speakers from the session to come up to the stage. If you have questions, you can come up to the front and speak into the microphone. Please state your name and your institution. Let's give them a second to get up there.
So, Alessandro Maturilli, DLA Berlin. I have a question for Dr. Colin. I didn't catch your name, I'm sorry. And I didn't catch your last slide because I'm blind to color, so I could not read what was written. But I hope that you wrote that you are open for collaborations because future steps, I come from spectroscopy world, would be to distribute those samples. So my question is this your task, your goal, and how difficult it is to produce grams of material for different planets and distribute them?
So in terms of the like the silicate material, I guess I'm not sure which of the materials are you interested in having distributed?
Well, from full simulants for planets to minerals. It's let's say we go in all the directions.
Sure. Yeah. Okay. So just in general, from that like method of creating the material.
Yeah.
So in that particular, those particular type of experiments are pretty small volume. They're like very small volume. So creating something that's a high pressure material, it's difficult to produce grams and grams and grams of something like that. So at the moment, that doesn't scale on this type of stuff that we do. We have other methods for creating materials, but like our lab isn't set up to create large grams and grams and grams and grams. Like 10 grams is a large batch for us, just because we're more focused on the chemical properties of the things, which scale when you go from a small sample to a large one. But there are other labs at JSC that do focus on the bulk creation of those samples. So.
Thanks.
Hi, Austin Patridge from UTSA. I'm a master's student there. I had two questions. I guess my first one was for Dr. Iacovino. That was actually super cool to see, and my advisor routinely scolds me about how expensive platinum is, so it's really cool that you can do this with stainless steel. But I was curious because, I mean, your method seemed to be working, but I was curious how it actually quantifies. Have you actually, I guess, plotted your steel 304 as like a buffer yet? Like, where does that, in the log scale,
Yeah.
where does it plot? Is it near iron woostite, below?
So that's really complicated, right? So it's a range, and it depends on the silicate composition, because it's the reaction between those two that's giving you the final answer of where the oxygen fugacity is. So it's going to depend. The other issue is, when you're calculating that value, we calculate it based on a buffer because we know those thermodynamic properties. We don't very well know. When the silicate melt is one half of the reaction, it means we need to know like the equilibrium constants of chromium oxide in silicate, which we don't know very well. So we can do iron and iron oxide pretty well. It's pretty well studied, but it's very difficult to calculate, basically. There's huge error on that. So we think it's somewhere between iron woostite -1 as potentially as low as iron woostite -8. That's going to depend on how well we know those properties or can figure them out, and the silicate composition. So in my mind, we might take, say, a mercury relevant or a lunar relevant composition, a 304, and we figure out what works and sort of offer that to the community and say, oh, you're going to work on 15555. You use this steel, and you measure these things as sort of a standard in your own lab, and this is what you'll get. So kind of creating like a set of standards that we can say with confidence, this will give you this FO2 or close to it.
No, super cool. I'm excited to see where that goes.
Awesome.
And then
Thank
my
you.
second question was for the Gator team. So I understand a lot of times regolith and the cohesion of it is really attributed to being like almost like wet sand. I don't think any of the astronauts actually said that, but it really is really sticky, and especially because of the agglutinants, it's really cohesive with depth. For your test bed, do you have glass or agglutinants in your simulant? Do you plan on maybe wetting it to try to replicate that really high cohesive effect to maybe better replicate the soil?
Well, the cohesive properties of that was LHS1, and also for LMS1, the cohesive properties actually match very well with what was measured, at Apollo 15 for the MARI and Apollo 16. For that, I could direct you to those papers. I'm involved with those papers, several in the last year. So the geotech properties are very well characterized. And actually, there's a good paper came out last year by Dotson et al. I'm not on that one, but that one characterizes many of the exolith simulants for cohesion, and it's also an exponential relationship, just like I showed for the density profile, and that makes sense, right? And then also there's a correlation, I think it's a quadratic between the angle of internal friction as well for the simulant. And so we use those values when we're running our tests and everything like that. So you don't need to wet it. I could go into more info about the moisture content and using dried versus undried. We've seen some slight changes. LHS1 typically holds about 800 ppm absorbed moisture, and of course it's more for Mare. We're talking about 3,200 or so. But those are interesting questions. And we also, there's a dehumidifier in Ryder, so we try to keep that humidity down as much as we can. So no, there's no need to wet it. The geotech properties are pretty close, actually.
Okay, good.
I can
Thank
show you charts on that.
Yeah. Thank you so much.
Yep.
Okay, we're going to take an online question.
All right, the first online question is for the first speaker. It is from Natasha Johnson, and it says, I may have missed it, but did you show a comparison chart of the time versus temperature, and was the difference significant?
Yeah, that was like one of the last slides, so I didn't really have time. I kind of skipped everything. So when we compare like the 30 minutes of mixing in cold temperature versus just like no time at all, it's kind of what you get for the normal temperature as well, where it's like it just shifts and the mixing is more different. And then when you compare like cold temperature mixing versus warm temperature mixing, the cold temperature mixing is like much the peaks are too shifted, so the colder ones are smaller on average. Hopefully that answers the question.
Hi, Christina Buffo, Georgia Tech. So I have a question for Sam. I don't know a lot about radar, and I also am very hesitant to add anything else to your extremely thorough but labor-intensive methodology. But I am curious, how do you think your results would change if you added carbon dioxide ice, whether as a separate layer or mixed in with the water, or even mixed in with the regolith simulant?
So in the polar layer deposits specifically, it's around like 95% water ice, and the rest is likely dust. And so I don't think we're going to be seeing these CO2 levels mixed in there. It's going to just be like a CO2 kind of frost that forms on top of the PLDs. And so it is something we could test, but it would just change the permittivity values a little bit, but it has similar, CO2 ice has pretty similar permittivity values to water ice. And so it wouldn't change too much, in my opinion.
Okay, so like it might change the intensity of the patterns, but not where they are or how they're reflecting.
Yeah, sort of. So like the main contributor to where these reflectors show up is the dust concentration. And so the dust concentration has like the permittivity in 3 to 4, while water ice and CO2 ice are pretty low, around like 1 to 2. So that would be the main difference.
Cool, thanks so much.
Hi, I had to step out for a minute, so I hope nobody asked this question already, but this is for Kayla. Would it be possible to use a steel that had less chromium? And even better than that, do we need a planetary core simulant that you could use as an inner capsule that would have appropriate amounts of iron, nickel, and sulfur?
Yeah, that's a really cool idea. I like that a lot. I mean, I think the advantage of the chromium is that if you can remember the oxygen vigacity scale I showed, that was the biggest thing pulling our oxygen vigacity down to the left, because steel is obviously mostly iron, and we want to be able to get way below that. So iron and nickel are relatively oxidizing, especially nickel. So chromium was the thing that was supposed to help us pulling it all the way down. If you stable, and Noah could tell me what the temperature is, he's probably watching online, there at a certain temperature is when you switch from austenitic to this non-austenitic property, which is where you shed chromium. So at lower temperatures, it's not an issue. But the sulfur thing is really intriguing, because sulfur just like complicates everything, and it bonds with everything. And if it comes out as a gas, then it gets into your instrumentation. And so like, I don't know, I need to think about that. But there's a lot of steels that have like a little bit of sulfur in them, and it can have a huge effect, and it's a huge redox. It's really good at moving electrons, right? So I love this idea of like your mantle is your silicate inside and your core is surrounding it. now you have the inside of a planet. I don't know, I'm going to think about that. That's a really cool idea. Thank you for that.
Cool, thanks.
NOAA is online and they say 1200 to 1300 degrees Celsius.
There you go. Thank you, Noah.
Hi, Christian Chan, APL. My question is for Sam. So great work so far. I'm curious as to whether you've considered the use of like radar modeling, for example, like thin film reflectivity to constrain the parameter space of your experiments, because it seems like you can change the different like layer configuration, the number of layers, thickness and depth, and that can have an overall effect on the overall observed reflectivity, and whether you'll be actually sensitive to those types of reflectivity powers in the radar data itself.
Yeah, that's definitely something we're going to be looking at. I want to just get through all my experiments first before I start running a bunch of simulations, but we're definitely going to be looking using like GPR Max and some FDTD simulations to make sure what we see is what we get.
Yeah, I mean, I think there are also like just some more simpler analytical models that you
Okay.
can actually do to at least constrain the parameter space and a number of experiments you would have to run, because otherwise you're changing like a really large, I don't know, a lot of variables kind of in those
Yeah.
experiments. But I'm happy to kind
Yeah,
of chat with
definitely.
you more
Yeah, I'd love
afterward
to
too.
get to know what those are, but thank you.
Yeah,
Yes.
definitely.
Jiawei Wang from Cornell University. I have a question for Alice. So the question is, in your experiments, you see the thawing particles growing during evaporation, right? So do you think the evaporation rate will matter? Have there been any studies talking about the growing under different evaporation rate?
So I do think it will matter because that's like directly tied to how long you'll spend in the liquid itself. I mean, I haven't tried it yet. I mean, like we put it in the fridge, right? So that kind of changes your evaporation rate a little bit. But like I personally have not tried doing like different liquids that maybe evaporate faster, like forcing it to evaporate faster. And I don't know if anybody else has, but like just on the basis that we see that time makes a difference alone, the evaporation rate will likely make a difference. Yeah.
So in your experiments, you did it like naturally, just like naturally evaporate.
Yeah. So we just let the hexane just evaporate naturally, like through the air. There's no like forcing of the air on it or anything like that.
Okay, gotcha. Thank you.
We have another online question for Sam. It is asking if the plastic wrap affects the results, assuming it is not removed prior to the measurements.
The plastic wrap to make sure the dust doesn't enter suspension. Is this what we're talking about?
I believe so.
Yeah, it's removed before water freezes. But yeah. But yeah, like we can put the plastic wrap down and add the water on so the dust doesn't enter suspension, and then I can remove it carefully. And so.
And another online question for the last speaker. It says, just curious, is this type of wheel/tread impact for experiment study also used for terrestrial purposes, as might be applied to sensitive ecological areas?
As far, yeah, if you're talking about cone penetrometry, that actually is a well-known method for forestry science. So if you are interested in the properties of the soil for trees, tree roots and things like that. And so a lot of these the one that I showed is a field electronic. Of course, you got the wedge penetration. You've got an ultrasonic sensor that senses your depth as you go, and it's got a load cell that records the pressure or stress as you're going through the soil. So yes, these are used in terrestrial applications. Road construction, airport construction. There's larger ones, there's truck mounted ones, there's ones where you drop, 8-10 kilogram weights and you keep doing that. So yes.
Thank you.
Can I use my speaker privilege and ask a question? I have a question for the Zanes work that you did. So that was really, really neat thing that you're looking into. You talked about the sulfate versus sulfide, and that you see sulfides in the Martian meteorites, right? And you were seeing sulfates in what you were measuring. Have you compared your results to things from either experiments or measurements on the Martian rovers? So I think there are work that is looking at sulfates from the rover perspective. So I wonder what you thought about that.
Thank you so much for that question. I haven't looked super deeply into that just yet. This project is very new. I've just started it. But yes, from just the kind of quick overview of what I've seen in literature, I was looking more into the Martian meteorites because there is a lot of just data out there because they've been looking at them for a very long time. But yes, for sure, I will be looking into those rover findings a bit more because yeah, I definitely do know a little bit more about phosphorus than sulfur. So I'm excited to get more into that and kind of gain more knowledge and add to this project. But yes, very good point. Thank you so much. Did you have any other? Because do you have anything else? Oh, perfect. Yeah.
Yeah, just like another quick question. Like it's interesting to me when people work on the simulants and then we're like taking the simulants that we've made and then figuring out what's in them. So what, like, do we not know the form of the sulfur that was added? Like, what, you know, why you have to do these measurements if we've made them ourselves, kind of is my question.
No, that is a very good question. Awesome point. So just kind of the lab created simulants, right? It is a bit of a hodgepodge of things getting kind of mixed together. This is a regolith, right? So it's very just a mineral heavy regolith, right, mixture. And so, yeah, online you can see a lot of what's in there. But and just kind of on like a very broad mineral kind of concentrations, like, yeah, Yes, yes. So yes, yeah. So they take what we found from these Martian meteors or from the samples that we've gotten from the moon, and I'm sure you have plenty to add to that too. But from what I know, and you can completely correct me, it's just like their best representation to match what they found more on a mineral bulk level. I know there's a lot of these regoliths are made for the more engineering realm, and so it's actually very interesting to kind of jump in there and look at the like nutrient speciation. If you want to talk about this at all.
Yeah, I'll just chime in that so Exolith Lab used to produce the simulants, and there's a private company now that split off and formed their own startup that's now producing the simulants called Space Resource Technologies. And if you're interested in these simulants, you know, they're sourced from natural minerals. I haven't had much experience with the Mars Global simulant, but for the lunar ones, and for all the simulants, I can tell you on the website, there's really detailed spec sheets that you can download. They typically have the bulk chemistry, the modal mineralogy. You can find out information about where the natural minerals or rocks that they're mixing are sourced from, particle size distributions, and actually not just like the bulk composition and mineralogy like I described, but also some information about geotechnical properties as well. So those spec sheets are a nice resource when you're fishing around to see what you want to buy and work with. So.
Perfect. Thank you so much. Was that all your questions? Okay, perfect. I also had a question if we have time.
Is it for Pratik?
Is that the first speaker?
I'm going to ask one question to Pratik first, and then you can.
Of course.
Yeah. Pratik, you mentioned doing mid-infrared measurements in the lab, and I was wondering if you've seen any of those spectra and if you see similar trends in the band parameters that you're finding in the visible and near infrared spectra.
Yes, I did see some trend, but I can't speak a lot about it because last time when I plotted the TiO2 versus the asymmetricity or CF feature and MgO versus CF feature, so they were like totally opposite trend. And I don't know the reason why it was happening, because 2 days ago there's a poster session on newly open Apollo 17 glass beads, and they have a straight line feature with MgO and CF. So a lot of new trends, like not new trends, new weird trends are coming. So yeah, but there's two things are clear, that titanium and iron, these are the deciding factor actually for all the CF or band parameters for VNR classes.
Awesome. Thank you. Yeah, now you can ask your question.
Okay, perfect. This question is for the first speaker. Yes, I really liked your presentation. Actually, all of y'all, I'd like to say, great presentations. Thank you. Yeah, so your kind of coagulation of what you're trying to achieve with these very, very small particles, I'm assuming from your just kind of putting into water, you were just kind of trying to get that flocculation from just van der Waals and kind of these very simple mechanisms. Have y'all tried doing this experiment just at different mixing speeds? And were y'all ever thinking about adding a coagulant to kind of up to that, those kind of flocks that y'all are trying to achieve? Sorry if this is a little outside the scope.
No, that's a good question. So we didn't, I thought about it for a while, like doing different mixing speeds, like before you hit turbulence. So we just do like Reynolds number, like turbulence, and then that was it. Like, I think we even go a little bit higher to make sure it's turbulent, but like, I thought about it for a little bit, and some of the studies kind of suggested, like some of the Earth studies in rivers and stuff, kind of suggested that if you did that, it wouldn't really work. So for this, we just wanted to make sure, like, okay, does it work or does it not work? So I might go back and see, like, okay, what is kind of the limit for that? For the coagulants, we didn't add anything, and I didn't have any like plans to do that because it's kind of difficult to think about what would be on Titan and act as like a coagulant. Um, but I do know there's people who are like working on trying to figure out the exact kind of lake compositions because that's not even really known exactly. I mean, we know it's like methane and ethane, but you know, it's just whatever's the dielectric constant. So, but no, I haven't really thought about adding that at all.
I didn't want to have Pratik feel left out, so I've got one for you. So I noticed when you were showing your spectral analysis on your 1 micron band, your continuum wasn't on the shoulders. It was maybe halfway down the band. And in my work, you know, doing band centers and depths and things, it's like you fit the continuum to the shoulder. Is that standard procedure where yours was for the asymmetry analysis?
Coming to the continuum procedure, so what I found when I was fitting this continuum line, so if I was selecting the shoulders, then my fit was not good. Yeah, I can use the higher polynomial, like fourth order polynomial, fifth order, it will fit, but I fixed third order polynomial for all of my,
Third order.
45 micro and 125 micro. That's why I have to change the type points. And it was showing a correlation, like a similar analysis with the previous analysis done with the actual Apollo classes samples. And yeah, and one more thing, like for Apollo, for M-cube spectra, it was totally different actually. I have to go for the fourth order polynomial because it was so noisy. Yeah, so it changed because I fixed a particular polynomial order for all of the samples.
Thank you.
We have an online question for India. If you had unlimited resources, would you suggest altering any of these simulants to better mimic observations?
Oh, that's an excellent question. I would have to think about that. If I had infinite resources. Probably, yeah. There were a few things lacking that I saw in those simulants from what I've seen on the literature. Definitely those stable sulfides. Yeah, so there's a lot of reduced sulfur on these planets, especially since there's these limited oxygen kind of environments. And though that can kind of be a harder thing to achieve, and just creating these simulants, especially since we kind of mine them off of the earth and put them together. But definitely thinking more on the sulfide. I didn't see a single sulfide in any of these. And then just, yeah, I think maybe adding some of the more relevant phosphorus species. I'm still looking into the specific mineralogy, but excellent question.
Yeah, we have time for one more quick question.
Hi, my name is Lorraine. I'm at the University of Central Florida. My question is for Mike. So regarding the kind of like the simulants and the rover wheels, are there plans to do like other simulants and like outside of the moon? So for example, if you wanted to do like Mars and stuff like that, and how like beyond Mars as well, like are there plans for expanding the reach of the facility?
Yeah, you know, we have those simulants that would be in a very expensive undertaking, you know, because I'll speak for Ryder first. So, you know, with the split off of the private company Space Resource Technology. So, you know, Exolith now owns the Lunar Highland simulant that's in Ryder and also in Crater. You know, Ryder holds, if you're doing a 35 centimeter deep, you know, column or something, you know, that's about 2 metric tons of simulant. And then there's 125 metric tons in Crater. And the Crater one holds a LHS-2E engineering grade. Both, there's minor differences. The geotechnical properties aren't really affected. And I won't go into the details there, but you know, we would have, if you were interested, say, in Maury simulant and Ryder for experiments, you know, we'd have to work out a deal to purchase that simulant. And so we don't, you know, own that right now. And then the Mars simulant, I believe, is even more expensive. And so that would be a pretty expensive undertaking. But when it's large quantities, you know, they're willing to deal with you.
Thank you.
All right, let's thank all of our speakers again. And that concludes the session.